In section 6.4, we're going to look at the general exponential and logarithmic functions. In the previous sections, we started by talking about the natural logarithmic function, and we also looked at the exponential function. So we're just going to generalize those to any kind of exponential function, not the ones that have base e necessarily, and to any logarithmic functions, not the ones necessarily that are natural logs, again, those that are logs base e. So we're going to begin with our definition of exponential function with base a. So that is our first definition. Notice the structure of that function is like e to the x. The base is any valid base a, where a has to be positive and different from 1. The reason base has to be positive because the function is not going to be real if the base is negative. It cannot be 1 because if the base is 1, we get a constant function. 1 to the x is 1. So for those reasons, we have restrictions on a. The other thing that's interesting here is how you can rewrite exponential function in this form, e to the x natural log of a. That's also permissible to write, and that actually follows from one of the properties of logs that we have, or exponential functions I have, is actually this property, e to the natural log of u is u. Okay, so if we have e to the x ln of a, then I can rewrite this as e to the natural log of a, bring x to the exponent in the argument, and that's what that would look like. So instead of u, we have a to the x. If I let u be a to the x, then I can write this as e to natural log of u. And I just stated that that's one of the properties of exponents. E to the natural log of u is u. Therefore, we just show that e to the x ln of a, this expression is indeed a to the x. Okay. And there you go. That's the next step. So that's just the general exponential function with any base. Next to that, we have a theorem which recalls the properties or laws of exponents. Here you recognize the familiar laws. You have multiplication rule of exponents, you have quotient rule, and you have these 3 power rules of exponents. All right. Theorem 2 tells us about the derivative of exponential functions, where we have a to the x. The derivative of a to the x is a to the x itself times the natural log of a. Now the proof of these, we're just going to kind of wave our hand over the proof, and in the interest of time, we're just going to state them without the proof. But the proofs are in the book if you're interested. Next, we're going to look at the derivative of exponential function, where the exponent u here is now a function of x itself. So u could be a function of x. In that case, you get a repetition of the exponential function times natural log of a. So that part of it looks just like the previous part, a. And then, of course, we have chain rule, du dx, since u is a function of x. So that's the more general form of the derivative of a to the u. And then from that, we can bounce off of that and actually come up with the antiderivative of a to the x. So here the integral of a to the x dx is going to be a to the x divided by natural log of a. And you can verify if you take the derivative of this, you get exactly a to the x. Okay. And what else? So remember, it's important, the natural log of a in the denominator of the integral, and the natural log of a that appears in front as a factor in the case of differentiation. And finally, we have these 2 ideas. First, we have a definition of logarithmic function with any base a. Base must be valid, of course. Remember, base has to be positive and different from 1. So This is just definition of logarithmic function, y equal log base a of x, if and only if x equals a to the y. That's just general logarithmic expression. And then we look at the derivative of logarithmic functions with any valid base a. So the derivative of log base a is 1 over x ln of a, and derivative of log base a of u is 1 over u natural log of a, and chain rule times du dx. So those are the things that are in this section, and let's take a look at the exercises. And in the exercises, we're just going to look at the ones that are circled. Okay, so let's begin with exercise number 4. So let me write these down. Let's begin with exercise number 4. So in exercise number 4, in this section 6.4, the question is asking us to rewrite, so we're section 6.4, 6.4. So the equation is, or the expression, the function is x to cosine x. And the question is asking us to write it as exponent with base e, So this goes back to the very first definition that we had. So I can write this as e to the natural log of x to cosine x, and that's going to be e to cos x ln of x. Okay, again, I'm using this property that e to the natural log of u is u, that. Okay, now again, we can actually write it also. The other form we had here was in this form, the very beginning, where we defined a to the x. We called the function a to the x to be e to the x ln of a, right? Ln of natural log of the base. So you can also use that directly. Okay, let's take a look at exercise number 8. Is the one that I selected next on the list. So in exercise number 8, we want to do the same thing, kind of, except the question says evaluate the expression. So in problem number 8, we have log base 3 of 3 to the pi power. Okay, so we can actually write this as, using the properties of logarithms, bring the exponent and the argument in front of a log, so that's log 3 base 3, and that's just pi times 1. Remember, if the base of the logarithm and the argument of the logarithm are the same, then we just that's just 1. So the answer to this is going to be simply pi. All right. Pretty easy, straightforward. Exercise number 10 is asking us the same thing. Write the exponential equation as an equation using logarithms. So in number 10, part A, we have 8 to 2/3 equals 4, and we want to rewrite it in log form. So in logarithmic form, we put log. The base that is 8 is going to show us a base in the logarithmic expression. The answer, which is equal 4, that becomes the argument of the logarithm. And 2/3 is the answer to the logarithm. Okay. So this reads log base 8 of 4 equal 2/3. So that means 2/3 is the exponent to which you raise the base to get the 4, in this case, the argument. That's part A. In part B, we have 16 to negative 3/4 equal to 1/8. So to write it in logarithmic form, we carry the base to the base of the log, put 1/8 in front, and the exponent to which the base is raised is the answer to the log, -3/4. Okay, and there we have that structure. And that was exercise number 10, part B. Next, we're going to take a look at exercise number 12. The one I had circled was number 12. In number 12, the question reads, write the logarithmic equation as an equation using exponent. So we're looking at the utility of logs and exponential functions, how you can go from one to another form. Equals 1/2. So again, it's like doing number 10 in reverse. So first, the base 49 becomes base of the exponent. The answer is the exponent to which you raise the base to get 7. Okay, and there you go. We're done with this one. 49 to 1/2 is 7. So that's like the square root of 49. That was part A, and in part B we have log of 0.01 equals 2. Now one thing, if you recall, if the base of the log is not written as 10, we call that a common log, right? Common logs are logs base with base 10. So we can rewrite this in exponential form. Here's the base, right? The answer is the exponent you raise it to get the argument. That's -2. So that's 10 to -2 equals 0.1. There's the answer to part B of this exercise. Next, we're going to jump to number 24. If we were really interested in the calculus of these, that would be like derivative and the integration in this section. In exercise number 24 is the beginning of differentiation. So the question reads, differentiate the function. So in this case, a function of u is 2 to the power of u squared. Okay, so the derivative of this, call it f prime of u, you repeat the problem, right? For the exponential function, the derivative is the same, and then you multiply it times the derivative of the inside, okay, function, which would be in this case u squared. So that derivative is, let me write it, that's 2u, that's the derivative of u squared, right? And we also have that natural log of base, ln of 2 in this case. Whatever the base is, you have ln of base. Some put it in front, I put in at the end of the expression, but I'll go ahead and now simplify this one. We can write this as 2 ln of 2. Okay, and I'm going to put it in parentheses so we don't by mistake multiply the 2, that's the argument of a log, by the next expression, which happens to be u times 2 to the power of u squared. And there we have this one. Okay, that is number 24. Next, differentiation problem. Let's take a look at exercise number I have 28 here. In exercise number 28, we want to find the derivative of 2 to tangent of x. 2 to the tan of x. So remember, when we do the derivative, there's going to be a natural log of whatever the base is. In this case happens to be 2 again. If that was a 5 to tan x, then it will be natural log of 5. It will be ln of the base. So there's ln of 2. So what else we do next? Sorry, I'm doing number 30 here. That's fine. Let's do number 30. It was a good thing I glanced at the book. This is number 30 actually. I haven't circled this up there in my notebook, but that's fine. So there's ln of 2, and then we need to repeat the exponent. The derivative of exponential function is themselves, and then derivative of tangent. which is secant squared. And there you have it. There's nothing I can do here. That's the answer. Now let me do 28, like the one I had intended. In number 28, g of x is x e to the x. Actually, it's x to the e times e to the x. Now, got to be careful here because remember, x to the n, the derivative of x to the n is nx to the n minus 1. And this works with exponential functions also. X here, the base, doesn't have to be x. It could be, oh, actually it has to be x. The exponent n no longer has to be an integer. It can be any real number. Okay, so the first product, x to the e, we're going to use the power rule of derivatives in that. So it's going to be ex to the e minus 1 times e to the x. That is, we have to use the product rule, of course. So I did the derivative of the first by second plus first times derivative of e to the x, which is itself. And actually, just so you know, there is a natural log in there, but it's ln of e, okay? In the general exponential function, we have a natural log of base, but ln of e is 1, so that's why you don't see it when you take the derivative of e to the x. We just say it's e to the x. Okay, and let's finalize this one. Therefore, g prime of x is going to be, let's see, I'm going to factor x e to the x. Okay, I'm going to factor x to the e and e to the x. That's this expression. When we factor that expression, we get 1 plus, and same thing is being removed from the first term. So e to the x is being brought out, and also x is being brought out. Okay, so when we do that, we're going to get e to the x. Okay, and that should be the answer to this one. Okay, so hopefully, again, you follow the factoring. Let me focus on that for you a little bit here, actually. So that's e, again, x to e times x to negative 1 times e to the x. I'm factoring x to the e, which is this part, and e to the x, which is that part. Okay, so when I factor those, they're literally removed. All that remains are e times x to negative 1, and x to negative 1, you can write it as 1 over x, and hence the fraction that I got. Okay, and there you have it. So we're done with this exercise number 28, and the next one I had in mind was exercise number 36. In exercise number 36, we have y is equal to x squared times log base 2 of square root of x squared minus 1. Okay, now for this, again, we're going to have to use the product rule, but maybe we can simplify this one because it is log base 2. Okay, so it's not a natural log. Maybe if we write it in terms of a natural log, it would be easier. So let's do that. What I'm going to do is I'm going to use the change of base formula on this one. Okay, now the change of base goes like this. If you have a log base a of m, you can rewrite this in log m base b over log a of base b, same base b, as long as these are valid bases, again, of course. So I'm going to write the log base 2 as a natural log of square root of x squared minus 1 over natural log of 2. So in other words, I'm choosing to go with log base e. Okay, you can go common log, that doesn't matter. But natural log works nicer in general in calculus courses in integration and differentiation. So here, again, ln of 2 is a constant, right? So we can actually factor that, right? And I'm going to rewrite the ln. So this is what I'm going to get, x squared times ln of x squared minus 1 to 1/2 exponent divided by ln of 2, and then using the power rule of logs, I can bring the half in front of a log, right? That's what I'm doing. 1/2 brought in front of x squared, ln of x squared minus 1 divided by ln of 2. So I'm doing some upfront simplification, so it's going to make it easier for me to find the derivative. Now I just have to find the derivative of x squared times ln of x squared minus 1. You see how easier that is, this expression? The front fraction in front, that's just a constant. And in fact, 2 ln of 2, if you want, we can write it as ln of 4. But let's leave it like that for now. Okay, now I'm doing y prime. Here's 1/2 times ln of 2. So we're going to do product rule, derivative of first, which is 2x times second plus first times derivative of natural log 1/x squared minus 1 times chain rule, the derivative of the inside function is going to be 2x. Good. So we have done it that way. And let's see, next, here's 1/2 ln of 2. Let's see, what can we do here? Okay, I can actually factor now an x out of these two expressions. There is a 2 as a factor in both of these terms, and there's a 2 as a factor in the denominator in front. So those 2's actually can cross out. So I'm factoring the x. I'm crossing these 2 out, the 2's out, and factoring an x. So this is going to make this x divided by natural log of 2 times ln of x squared minus 1 plus x squared divided by x squared minus 1. Okay, and then if I distribute the fraction to the binomial, let's finish it off that way. So the denominator is going to be x squared minus 1 times ln of 2. The numerator is going to be x, and then we have x squared minus 1 ln of x squared minus 1 plus x squared, right? That's what we will have, and that is the final answer there. The reason I have x squared minus 1 in front of natural log is because the LCD here, the LCD is x squared minus 1. So I'm going to multiply top bottom of the natural log, rewrite it as a fraction with the LCD. That's what that is. And we're done with exercise number 36 here. Next one on the list, let's take a look at exercise number 42. In exercise number 42, here the question, let me write the equation first. Y is equal to sine of x 2 tangent of x. So tan x is exponent. So in other words, there you go. This is what we have. Okay, and this is exercise number 42. Now, the question reads, use logarithmic differentiation to find the derivative of the function. So when we do logarithmic differentiation, we begin by taking the natural log of both sides. So ln of y be equal to ln of sine of x 2 tan x. Okay, and let's see, this probably what they have in mind here is sine x to tan x. Yeah. That's fine. Let's see, so I can write this. In other words, I'm thinking this as sine x 2 tan x. That's what they have. So when I have natural log of that, I can bring tan in front. Okay, so maybe, see, in the book, this is how they have it, which is kind of sloppy. Because it makes a difference whether tan x is on the x or is on the sine. So I'm interpreting for the sake of this segment as exponent on sine x. In other words, this is how I see it. Let's work it that way. So we can bring tan x in front. That's going to be tan x times ln of sine x. Okay. And now let's take the derivative of both sides. We get 1 over y. Derivative of ln of y is 1 over y, and then y prime because of chain rule. Remember, we're doing implicit differentiation. To the right, we're going to apply the product rule. Derivative of first. Derivative of tan is secant squared x times ln of sine x. Right? And plus first times derivative of natural log of sine, which is 1 over sine x. Derivative of inside, which is sine, is cos x. Okay, so this is going to become, let's see, I'm gonna cosine over sine, that's cotangent. So this is actually the identity tan x times cotan x, which is 1. Oh, good. So that's just 1, right? I just have to work on this part. That part I can write it as the natural log of sine x. Oh, okay. And I'll also have to multiply. I'm going to multiply both sides by y. This way, the y on the left crosses out, and we have solved for y prime, which is what we want to do here. We want to find the derivative. That's y prime. Now, remember, y was sine x to tan x, right? And because I have sine, I'm going to rewrite my secant as 1 over cosine. So this will be ln of sine x divided by cosine squared x plus 1, and that is getting multiplied by sine x. Oh, it was ln. No, I was right. It's sine x 2 tan x, right? And that's about it. We can get LCD here, cosine squared x. So this is going to be simply natural log of sine x plus cosine squared x. That times sine x 2 tan x. There. So that's how that's going to come out. Okay. And again, if it's sine of x 2 tan x, we want to find that derivative. That's going to be more complicated. Yeah, for that one, the derivative of sine is going to be cosine x 2 tan x, right? And then now we got to chain rule find derivative of x 2 tan x. And to do this one itself, we're going to have to do logarithmic differentiation. Call that y. So you do ln of y equal to tan x ln of x, like that, and then proceed. So anyhow, I don't think that's what they have in mind, because that would be a little more complicated. Okay. We are done with number 42. Let's take a look at an integration problem. Number 44. The integral of 2 to negative x dx. Okay. So for this one, going off of the general integration rule, that's going to be negative 1 over 2 to the x times ln of 2 plus a constant. Okay, so I'm just following the integration property that we had for exponential function, more specifically this one. The integral of a to the x dx is equal to a to the x over natural log of a plus a constant. Okay. Now, of course, for this one, you can make a u substitution. That's where I got the negative from. If I let u be negative x, du is negative dx. So the integral becomes 2 to u, there's negative of du. So the answer is going to be negative 1 over 2 to u times ln of 2 plus a constant. And make the u substitution here. Negative x. Right, so let's see. Yeah, that's actually going to be 2 to negative x. Right? Oh, actually, no. It has to be positive. No, because it is negative, but because I'm writing it, hold on. Let me show you what. So that's the integral is going to be itself 2 to u divided by times 1 over natural log of 2 plus a constant, right? But then u is negative x. So 2 to negative x becomes 1 over 2 to the x. So that is correct. Yeah, that's fine. I'm good with this one. That's number 44. Next integration problem, we're going to look at number 48 in exercise number 48. The integral from 1 to 4 of 3 to root x divided by square root of x dx. Okay, now for this one, I'm going to make a substitution first. Let u be x, so du is going to be 1 over 2 root x dx, right? You can go through the process and see that is correct. Write square root of x as x to a half, take the derivative, and you get that. Okay, and let's see the limits of integration. When x is 1, u square root of 1 is 1. When x is 4, u is the square root of 4 or 2. So the integral is going to be that from 1 to 2 of let's see, with the choice of u equal root x, du is going to, oh, I have du, never mind. Let's see, so dx over 2 root x, and I almost have that. You can multiply, if you want, you can multiply the integrand, the denominator, by 2 and pre-multiply it by 2, so we get exactly, there you go, there's our du here, right? That's what I'm going to do. So this is going to be 2, 3 to u, and then du, there. And the integral of 3 to u is going to be itself 3 to u divided by natural log of the base, which is 3, evaluated from 1 to 2. So plug in the upper limit, that's going to be 3 squared. Oh, let me factor 2 over natural log of 3 out. So plug in a 2 for u, I get 3 squared 9, minus plug in a 1, you get 3. 3 to the first is 3, 9 minus 3 in parentheses, 6 by 2 is 12. So the answer is 12 divided by natural log of 3. And there you have number 48. And let's take a look at number 50. In number 50, the question again asks us to integrate square root of log x divided by the whole thing divided by just x and then dx. So for this one, I'm gonna let u be log x. This is common log because base is not written. Derivative of log x is going to be 1 over x times natural log of the base, which is 10. Again, where does the 10 come from? That's the base of the log, and that's what this becomes, ln of the base. Okay, and that's it, times dx. So let's see, we do have dx over x, so if I multiply both sides by a natural log of 10, ln of 10 du is dx over x, and that's exactly what I have in the radicand. So I can write the integral as square root of log, that would be u to a half, right? Hold on, gonna put ln of 10, that's the ln of 10, and then write u to a half. True, that's gonna be u to a half and then du. Good. Now the integral of u to a half would be u to 3 halves divided by 3 halves, so I can write it as 2/3 in front times u to 3 halves plus a constant, because these are indefinite integrals. So all said and done, going back to the original variable of integration was x. So we're going to have to end up with x. So that's 2 natural log of 10 over 3 times log x to 3 halves. I just changed my substitution for u, which is common log. There you have it. Now if you want, this is fine, this is good. But if you want, for the die-hard, you can change the common log here to ln of x over ln of 10. That's log x in base 10. You can do that. Actually, interesting. So there's a natural log of 10 there. So let me do that actually. This looks promising. So I'm going to write 2 ln of 10 divided by 3 times natural log of x to 3 halves divided by natural log of 10 to 3 halves plus a constant. Now ln of 10 to 3 halves, let me rewrite it. There's natural log of 10 over 3, nothing with the numerator, we'll keep that alone. Now in the denominator, if I have, like, for example, if I have x to 3 halves, that would be square root of x cubed, wouldn't it? So that's like root x, root x, root x. Well, 2 of those make just x. Well, natural log of 10 to 3 halves, that's just going to be ln of 10 times the square root of natural log of 10. I'm following exactly this form. And there we go. Cool. So let's go with this option. It's nice, it's simplified. We love simplifying expressions in math, don't we? Ln of x to 3 halves. And let me extend the fraction line, and I have square root of the natural log of 10 plus a constant. There you go. That was a good exercise. Number 50. Okay. And let's see, I had a couple of more, right? Number 58. Let's take a look at number 58. In exercise number 58, the question reads, find an equation of the tangent line to the graph of y equal x log x. This is number 58. Y equal x log x. We want the tangent line at 1, 0. Tangent line. Okay, now remember, to find the equation of a tangent line, whatever the graph at that point looks like, there you go, this is what we want. We know that this is going to be y prime, which is slope, right? That's the slope, the slant of the tangent line. And then of course we need a point which we are given, right? 0.10. And of course, let me be realistic, 1, 0, that's actually there you go, that's going to be the x-intercept. So at that point we have a point, if we have slope, we can use point slope form of a line to do this. So we do need to find the derivative to give us the slope. Using the product rule, I get derivative of first by second plus first times derivative of, again, log x, you got to be careful, that's log base 10, we don't write the base, so that's going to be 1 over natural log of 10, that's where ln of 10, where 10 comes from because of the common log, times derivative of log is 1 over x. Simplify this, I get log x plus these x's cross out plus 1 over ln of 10, so that's going to be the slope at any point, right? Now at 1, 0, that when x is 1, y prime evaluated at when x is 1 is log of 1 plus 1 over ln of 10, and log 1 in any base is 0, so this is just 1 over natural log of 10. So there's the slope, right, at 1, 0. Now, y minus y1 equal m x minus x1. That's the point slope form of a line. True? And that's going to be y minus 0. 0 goes in there. Slope is 1 over natural log of 10. X minus x1 is 1. And from this we get y is equal to 1 over natural log of 10 times x minus 1. Okay, now usually we multiply the coefficient, right? So it's going to be 1 over ln of 10 x minus 1 over ln of 10, and the reason is because we write it in mx plus b, the slope intercept form. And there you have it. That would be the equation of the tangent line at that point. Exercise number 58. Looking at one last one and we're done with this lecture. We're going to look at exercise number 62. In exercise number 62, the question: find the area of the region bounded by the graphs of y equal 2 to the x and y equal 2 to negative x, and lines x equals negative 2 and x equals 2. In other words, they want it from negative 2 to 2. That's another way to think about this. Now, in number 62, if we graph each of these, actually these aren't difficult to graph. There's your 2 to the x. This is 2 to negative x. And line negative 2 to 2, so that would be, let's say this is a vertical line at negative 2, and the other one is this one, x equals 2. There. Now we want, let's see. Again, let me read the question, number 62. The area of the region bounded by these graphs and between those two lines. So, let's see. It looks like this is the graph. That's the part for 2 to negative x and x equal to 2. And this is the other part right? It's going to be bounded by these graphs. Now, if I do kind of a better image of this, this is what it's actually going to look like. So I wanted you to see exactly what's going on, because my shaded region is so small. And this is going to actually look like that part of it. Okay, so this is my y-axis. Here's x. See right here, that's where that is. Okay, there's actually that part sits above the x-axis. Same thing for the other one. -2 and 2. So again, we want this region, which we can use symmetry, right, to get this. In fact, I'm going to do that. I'm going to use the symmetry of the graph. Why not? So the area of bounded region is going to be twice integral from 0 to 2. So I'm using this one. Let's call it A1. I'm using twice that area. Okay. Or you can do this one, doesn't matter. Whichever is easier for you to work with. Okay. So I'm going to go 0 to 2 but I got to be careful. 0 to 2, because if I go 0 to 2, then I have to go with 2 to negative x dx. Or if you want, you can go area is twice -2 to 0. I'm looking at this one, of 2 to the x dx. Either one would work. Okay, so let's stay with my first one. The area is twice the integral of 2 to negative, let me write it here, 2 to negative x dx. That's the one. If I let u be negative x, du is negative dx. So the area is twice 2 to negative x, that's going to be 2 to u, and then dx is negative du, right? Negative du is dx. The limits of integration: when x is 0, u is 0. When x is 2, u is -2. And I can switch the order of integration here, the limits, and offset is to change the negative into a positive. In other words, I'm going -2 to 0 of 2 to u du. And the integral of exponential function is itself, right? The derivative integrals are the same. You just have to divide by natural log of the base, which base is 2. So it's going to be 2 times 2 to u divided by natural log of 2. Okay, evaluated from -2 to 0. So that's going to make it 2 over ln of 2. 2 to -2 minus 2 to 0. 2 to 0, of course, is 1. So this is going to be 2 over ln of 2, 1/4 minus 1, right? 1/4 minus 1. And let's see, make sure I did this right, because we cannot get a negative area. Oh, I see what I did. Sorry, right in here I switched those orders. You put upper limit first, so it's going to be 2 to 0, and then lower limit next, -2 to. There you go, that would do it. That's going to make it now 1 minus 1/4, which is 3/4. So it's 2 times 3/4 ln of 2, or 3/2 ln of 2. 3 over 2 ln of 2. And if you like, again, this is purely optional, you can write this as 3 over ln of 4. Okay, because 2 ln of 2 is 2. I can put 2 in the exponent on 2. This 2 becomes 2 squared, which is ln of 4. Okay, and there you have it. And there is the answer to this one in squared units. And we we are done with this exercise. And with that, we are done, in fact, with this lecture.